Hello everyone, welcome back to this tutorial series on AVL. In this tutorial, we're going to try to put everything that we have learned so far and work with the airplane model that we have been building with its geometry, mass, and run cases, and try to understand how to run a simulation or analysis with the AVL using Aero console and examine our design so that we understand where we have to go back, configure our design parameters, and then do the iterations and again until we find the solution that we need. So in this tutorial, we will be covering the calculations that include the lift distribution, the Oswald efficiency factor, stall predictions using the lift distribution, trim calculations with some options for flaps down, which can happen when you are landing, for example, or you need additional lift, turn flights or banking, and looping flights, which has its own particular submenus in AVL. We will review the static stability that we discussed earlier in these tutorials and the concept of the neutral point and how we can find that point using AVL and the outputs and derivatives that we can get from the AVL using its analyses tools. We will also discuss the mode analysis or dynamic stability that we can run for our aircraft design. And we will look at the eigenmodes, interpretation of the eigenvalues, and what we can do with the visualization of these eigenmode and eigenvalues from the AVL mode analysis. So I went back and corrected the geometry file and the mass file because after running some simulations, the analyses, I figured that there were some issues with the design I had made in the previous tutorials. And as any design concepts, because I had not really tested the designs, I just came up with them as an arbitrary design, it was not giving me any meaningful results. So the simulations were not converging and were failing. So I went back to check what was happening with these designs, and I figured that I had incorrectly put a Y duplicate for my vertical tail, which resulted in undesirable conditions and performance for the aircraft I had designed. So I went back and I fixed by calculating the S reference, C reference, and B reference values. So I updated these to reflect the actual dimension of my design. I did not change the dimensions of the design, just updated the S reference, C reference, and B reference. I found the Y duplicate in the vertical tail that shouldn't have been there, so I removed that Y duplicate to fix that issue. And with these new calculations, I also calculate the aerodynamic center for this, which is the wing aerodynamic center, which should be where the wing starts, which is 10 centimeters, plus 1/4 of the chord, which is 30/4, and adding these up would be 17.5 centimeters. So this would be the location where the aerodynamic center of the wing is going to be. So remember these values as we're going to do the analyses on this designed aircraft as we go through this tutorial. So remember the aerodynamic center for the wing is 17.5 centimeters. Additionally, I went back and updated the mass file and I reduced the mass from each point mass having 5 kilograms mass to only 0.1 kilogram mass, because otherwise it would be a very heavy aircraft and we wanted it to be simpler and easier to maneuver. So I reduced this as well. You can check with various point mass values to see what gives you a better result if you are going to work with this design. But for now, we will be working with the point masses that are all now, instead of the 5 kilograms that were before, to 0.1. So these are the changes or the corrections I've made to the geometry and the mass files that we have been designing and working on for this tutorial. Now let's do a quick recap on some of the definitions for stability. We said in the previous tutorials, and you can go back and watch the tutorial that fully covered these concepts earlier in the tutorial series, that the neutral point is the point where the stability of the aircraft is neither stable or unstable. We said as the CG, or the center of gravity, moves forward, the stability of the aircraft increases and the aircraft is aesthetically stable. When it moves backward or towards the nose, towards the tail, the aircraft stability decreases. So the aircraft becomes or tends to become more statically unstable. There is a position in the middle where the aircraft is neither stable nor unstable. That is, the stability is neutral, and this point is known as the neutral point. The neutral point is fixed for a particular aerodynamic configuration of the aircraft. So based on the geometry file and the mass file, this is where you should be able to find the stability, the neutral point, and we will see where you can find this after you put all your files or import them into the AVL, where you can find the value for the position of this neutral point. Additionally, we said that we need to have our Cm equals 0 and Cm alpha or dCm d alpha negative for an aircraft to be statically stable. So we can check this as we go to our aircraft analysis later in this tutorial. Some other things to note is that an aircraft must be statically stable as a precondition for dynamic stability. So your aircraft can be statically stable without being dynamically stable, but it cannot be dynamically stable without being statically stable first. And from an approximate analysis, we can find the bounds for the location of the aircraft center of mass. So for our aircraft to be statically stable, we can approximately get the bounds for it to be behind the wing aerodynamic center and ahead of the fixed stick neutral point. So if we know where the aerodynamic center is, the wing aerodynamic center, which we saw for the design we have been working on, the correction, is now at 17.5 centimeters. And it's ahead of the fixed stick neutral point, which we can find the value of again using the AVL. We should have a statically stable aircraft, and we can analyze this. But this position should result in a Cm that is 0 and a Cm alpha that is negative. So if you don't have this condition, this would not be met, and this means that you won't have a statically stable aircraft. Now, how can we run the simulations? So first of all, you have to load all the files, and once you load all the files properly, you should be able to press the command X in the operation menu, and if everything is fine, the problem is not ill-posed or you do not have issues with the configurations you have set up, so the simulation can converge, you should get results for your solution. So let's see how this looks. So here I have the new version of the Aero console. I have added the ability to load the file directly here by pressing the buttons instead of typing the commands. So here I have two projects. The project we have been working on is test. So I've updated those files. I'm going to maximize this window. And when I click on the load geometry, what this basically does is it's gonna type in the command here, load test or load test.avl, and press enter. So I've automated this by just pressing this load geometry. So it is successfully loaded. As you can see, it is saying that it's read test AVL And in the configuration, it has a wing with a Y duplicate, it has an H tail with a Y duplicate, and it has a V tail without the Y duplicate. When I was examining what was wrong with my configuration before or geometry file, I found that the V tail had a Y duplicate, so I had to remove it to make sense or have a reasonable geometry file. And it also gives you some data on what are the loaded geometry conditions. So what are the number of numerical analysis data that we need? And additionally, what are the control variables that are included in this design, given how many control surfaces and of what type you have in your geometry design? Next, I'm going to load the mass file. So pressing the load mass button here is equal to typing mass test.mass in the command window and pressing enter. So I'm going to load mass. When I do that, it is successfully loading the mass file. Now that you see, I have the 1.3 kilogram mass instead of what I had before, because I have updated my point masses to have only 0.1 instead of 5 kilograms. And I have the updated center of gravity, location, and I have the updated inertia matrices. Now remember that if you update the mass file, you have to update your inertia and mass information for your run cases using the MSET. So before we do that, I need to first load my run cases. So to do that, I'm going to press the load run button. It is equal to typing in here case test.run and pressing enter. So if I click here, load run, it is reading the file here. I had 2 run cases, cruise and banking, and they are loaded successfully. Now, to be able to apply the new mass information, I'm going to type mset, and it's asking me which run case I want to apply it to. I'm going to press 0 because I want to apply it to all. And then I'm going to enter the operation menu with command upper, and I'm going to save my run cases. Press S. So it will ask me the file name is test.run. I say yes. It already exists. Do you want to override? Yes. So I'm saying yes by pressing enter on the keyboard. And now my run cases are updated. So I was able to successfully import my geometry file. I was able to import my mass file, and I was able to import my run cases and update my run cases mass information and save them again with the updated mass file. Now that I have everything loaded and updated, I should be able to start executing some simulation or analysis. So as we said, what you can do to execute the new simulation or run is going to be through pressing X to execute a run case. Right now, I'm in the run case, the first run case, which is labeled as cruise. So if I press X and hit enter, we go back to see what is happening. So we see that after 4 iterations, the simulation has converged. So we do have a solution. And it's giving me some information about the configuration of my plane, the reference values for my plane, which we said we had to update based on the geometry file, which was not updated in the previous tutorial. So that was one of the corrections we had done. It is telling us that it is running the cruise run case, which was the first run case from the 2. And in this run case, we have an alpha that is 5 degrees. And with this alpha of 5 degrees, we do have some total forces. So we have very small amount in the X and Y direction, but a larger amount in the Z direction. And we do have total CL, total CD, CD viscous, CLFF, and CYFF. And we do have the induced drag, and we do have the CDFF. So these are related to the sources of the drag, and you can see the induced drag is basically drag caused by infinite or lack of infinity for the wings, so the vortices that are generated at the tips of the wing. So due to the lift, so CL, there's the induced drag, and then you will have the FF, which is the friction portion, and you also see the Oswald efficiency factor, which here we said is the elliptical wing is going to give you the most efficient wing, which gives you the Oswald efficiency factor of 1. The closer you are to E equals 1, the better your wing design is. But here we see that for this design, the efficiency factor is only 0.1 or 0.11, which is very low, so we do not have a good efficiency for the wing we have designed. What we can do is we can try to increase the efficiency by making it look more like an elliptical wing by tapering it properly and changing the surface area. So that is one thing we can do to improve the efficiency of this wing. And we also can see where our control devices or control surfaces are standing for this condition, which was labeled as cruise or run case. And we see that our flap is at 0, so we don't have any flaps. The ailerons are deflected very mildly, but the elevator is deflected very much. And the rudder is not deflected at all. So with this, what we can see is that the ailerons are going to be used for balancing the roll, which is about the x-axis, the elevators about the y-axis or pitch, and the rudder about the z-axis. And if we look here, we see that the elevators are strongly impacting or are deflecting to be able to give us the minimum moment for or the trim condition for our aircraft. So we see that the CL, CM, and CN are all around 0, but CN is a little bit higher than the other two. But for CL, CM, and CN to be close to 0, we do have a lot of elevator or control input. If we didn't have an elevator on this aircraft, we would not be able to trim this aircraft. We would not be able to fly it stably. And because of that, it is very much deflected. Now, before we continue this analysis, let's go back to the slides to see what else we have here. So once we do the execution of a run case, we can see additional information by typing any of these commands. So we can type fn, fs, fe, or fb to be able to see the additional forces that are acting on the body. So if we go back to here, we can see that those commands are actually shown here. So we have SB, FN, FT, FN, FS, FE, and FB. So all these forces, in addition to the hinge moments and the strip shear moments, can be viewed or written to a file for further analysis outside of AVL. We also have the stability derivatives that we can look at, and we will look at them shortly, but let's go back to the slides. So the force and moment directions are in the stability axes, which are tilted up by the angle alpha or angle of attack from the body axis. So if you don't know the difference between the stability and the body axes, the stability axes just help us analyze the aircraft easier because it gets rid of a lot of the non-necessary derivatives and elements in the equations that we have to deal with. So that's why the stability axes were created. And the only difference between the stability axis and The body axis is just they are tilted by the angle of attack or alpha about the y-axis of the aircraft. And this is the transformation matrix from the body axis to the stability axis. And the following standard normalizations are used. So any of these coefficients for any forces and moments are basically those forces and moments normalized, which is divided by these items or values or terms, which basically non-dimensionalizes the forces and moments. And the usefulness or the advantage of these non-dimensional terms now is that we can scale them to any other design at any scale for that particular design that we have without having to recalculate a lot of the elements like any other non-dimensional analysis that you may have came across. We can additionally see the moments, and the moments we can see is going to be used or can be obtained from the ST command in the operation menu. And the overall look or formatting of how they should look as an output in the AVL is like this. So we can see the body axis or stability axis. So this should be body axis and the body axis and the stability axis. And then we have geometric, standard, and rate moments. So if we go back to here with the ST command in the operation menu after we run or executed a run case, I'm going to type ST, press enter. It says, do you want to output them to a file or just see them on the screen? I'm going to press enter to just see them on the screen. And we see that all these are calculated. So we can see, again, the information we had. We see the Oswald efficiency factor. We see all the derivatives. So these derivatives come in handy when you want to calculate by hand your stability, dynamic stability of your aircraft, or you're interested in the static stability, which basically is something you would see when you're looking at the Cm alpha, so moment about the y-axis. So we see here that the Cm alpha for this aircraft is currently at 4.12, which is a positive value. And as we said before, we want for static stability the aircraft to have a Cm of 0, which we saw the Cm was 0 with a lot of effort from the elevators, but we do not have the Cm alpha or the rate of change of Cm with alpha as a negative value, which is required for static stability. Now we can kind of see why that could be happening. Something else we can see in the stability calculation or stability derivative calculation is the location of the neutral point, which is x and p. So here we see that the x and p for this design is located at 0.26, and this is our neutral point. If we go back and look at our CG, so we have to go back to the mass file and we see the center of gravity. We see the center of gravity for this aircraft, based on how we distributed the mass, is at 0.5. And we already found that the aerodynamic center for the wing was at 17.5 centimeter or 0.175 meter. So comparing the 0.175 meter for the aerodynamic center of the wing and the neutral point for the aircraft, which is at 0.26 almost, so 0.26, and the center of mass, which is at 0.5, we see that the center of mass for this aircraft is behind both the aerodynamic center and the neutral point. We said that as a rule of thumb for the aircraft to be statically stable, it needs to be behind the center of gravity. Sorry, the center of gravity needs to be behind the aerodynamic center of the wing and ahead of the neutral point. We see now for this design that we have, it is behind both. So it is after both the aerodynamic center of the wing and the neutral point for the aircraft. And that's why we are seeing the Cm alpha to have a positive value. So to be able to change this, one correction we can do in the further iterations in the design is going to be to try to move the center of gravity by changing the location of the mass points or point masses that we have for the mass distribution between the aerodynamic center of the wing and the neutral point for this aircraft. If we cannot touch the mass distribution, what we can do, we can change the location of the wing and tail. So with that, if we have the masses on the wings and tail, the mass is also moving. So we will have the aerodynamic center moved, and we will have the mass center of gravity moved. And we have to go through these iterations to be able to finally fit the CG between X and P and aerodynamic center of the wing so that we can get this Cm alpha to be negative, so we will have a statically stable aircraft. We said that the static stability is a precondition for dynamic stability. Once we get to the eigenmode analysis later and we look at the eigenmode or eigenvalue distribution, we will see that because this aircraft is not statically stable, it also is not dynamically stable. So because it's failed to be statically stable, it does not have a dynamically stable condition as well. We also have the definition of the Oswald efficiency factor, so we can see how it is calculated in AVL. And the next thing we can see from the operation menu is the Trefftz plane. So what Trefftz plane does is it basically shows us all the available condition for this flight or run case with the coefficients for different forces and moments, the Oswald efficiency factor, and the alpha, beta, and Mach number, and the efforts of our control surfaces. So in addition to that, it is showing us multiple CL and alpha induced or induced angles of attack. So we see that this CL perpendicular or CLT or CL with this perpendicular sign, which we will get to as a definition for itself. As red, we have the orange line, which is showing the CL, and we have the CLC over C reference, which is kind of a normalized CL, and the alpha I, which is the induced alpha or angle of attack. And we can get this plot by going back to our simulation here and typing this T to get the Trefftz plane. So if I type T, what it gives me is this Trefftz plane. And as we saw on the slides, this is basically what I had hard copied and then imported as a vector graphic into my slides. But we can see this is showing us the same behavior or trend for the lift distribution over this wing. We see that it is at angle of attack of 5. We don't have any beta or bank angle. And we do have very low efficiency, and we have 0 moments, which we're trying to trim the aircraft. So that's why we have this really large elevator angle deflected at about 63 degrees, which is not really preferred. And we also see that we do have a continuous CL distribution or lift distribution. If you see that you do not have the continuous lift distribution, it may be because in your definition of the geometry file, you did not properly distribute the span-wise and chord-wise length for your lattice or grid. So maybe you should go back and check those. And that should be able to fix the distribution to be more continuous rather than discrete or discontinuous. So this is the Trefftz plane that we get some information about, and this is more so used for a quick overview of your important parameters for that run case, plus the lift distribution. Additionally, we should be able to find a stalling, whether this is a stalling or not. So to be able to get the drag polars or the CL alpha or CL versus alpha, which is used for the stall determination, you can use XFoil, which is another software by Mike Drela. And if you type in these commands in order, so the first one is just a NACA number if you don't have a NACA airfoil. In this geometry design that we are using, we have used NACA 2312. So that's why I have used this. And then following everything else, I was able to record the CL versus alpha in the polar.txt file and then import them into MATLAB and plot them. And this shows me that at an angle of attack of almost 14 degrees, where CL is 1.3 or almost 1.3, this aircraft would stall. So if I go back, I see that my angle of attack is right now at 5 degrees. The CL amount I have is 0.8, so it's a good amount of CL. And I also see that none of my CL is going to the amount or the angle of attack that it would be stalling. We want to keep all the CL below the stalling point. So what we see here is that the stalling can happen if we have at these sections of the airfoil more than 1.3 CL. So the orange line, we said the dash orange line is the CL. So we see at these sections above 1.3, whatever is in the middle of this airfoil section or wing is experiencing or maybe experiencing the stall. So to avoid this, you can change your flight conditions to bring everything below the stalling CL or angle of attack, and otherwise you would have to change your geometry or other flight conditions to be able to bring that back to below the stalling conditions. So that is how you can identify stalling for the airfoil or sections of the wing or the wing using a combination of the XFoil and AVL. And these are some of the definitions for the term we were seeing. So the CLT or the perpendicular CL is defined with these equations from the documentation that is provided with AVL by Mark Drela. And you can see all the elements. Something else is why should you use different things? So the reason they are provided is that depending on the type of geometry you're working with, whether it's high aspect ratio unswept surface, high aspect ratio swept surface, or strongly 3D geometry with rapidly varying chord and or sweep, you need to look at different CLs for interpretation of whether you're stalling or not stalling or what it can be. So the different CL or CLT elements or the normalized CL are to be used under different conditions or for different geometries in your design. Now, something else you can do when you're working with the AVL is the trimmed flight conditions. So We have two particular flight conditions, the trim flight conditions or the loop flight condition, which you can enter into with C1 and C2 command in the operation menu. But for any of these, you can also input manual data. What these trim condition flights help you with is recalculating the interconnected elements or parameters for flight for those particular trim conditions without you having to go back and recalculate those. If you were to manually input the parameters using the M command, you would have to know what is the relationship between the various, for example, velocity, the angle of attack, CL, bank angle, Mach number, and things like that to be able to properly set up a trim condition flight. Otherwise, you would have to use any of these trim condition flight menu options to be able to properly set them up and run them. So we see that, for example, for the trim flight condition setup, we have the C1 menu. In the C1 menu, we have the following properties that we can set up. So you can see the full properties with their definitions here, and you can always come back and double check. These information are from the AVL documentation provided with it by Mike Drela. So they are directly from the software and the author itself. But how can we actually set it up? So once you input that information into the C1 first menu, you will see if everything is properly set up, you will see these parameters. These parameters are for level or banked horizontal flight. And what you can do with them is you can change any of them, and anything else that is related to that particular parameter that you just changed will be recalculated for a level or banked flight condition automatically, and it will be updated. So when you're running this case again, you know that everything is properly set up without you having to go and manually set them up. So if we go back here, we're going to exit the Trefftz menu. We go back to the operation menu by pressing enter. We see that in the operation menu, we have the C1, C2, and M. So M is to modify the parameters manually. If I press M, it shows me all the parameters I can manually change. But I'm going to exit this. I don't want to manually change anything here. I'm going to enter C1, which is a level or banked horizontal flight. And I see that in this new menu for setting up the C1 or trim condition flight, I have multiple options to change various things. For example, I want to have a particular lift coefficient or CL during my trim condition. I want it to be flying at certain velocity. I can change the mass here directly, but it's better to just keep it as what you have in your mass definition. I can change the air density. We can see that the air density here is set up to low amount. If we were to, which is at higher altitudes, if we were to, for example, fly at lower altitudes, at sea level, for example, we would set this to sea level, air density of 1.25 approximately. And you can change the gravitational acceleration, the turn radius, if you are doing a turn flight trim condition, and the load factor as well. And you can set up the center of gravity XYZ as well. But it's better to leave these to be read from the mass file to not mess up your simulation. Now, to show you how this will automatically change things is, let's say I want my velocity to be instead of 10 meters per second to be at 20 meters per second. So I'm going to press V for velocity, and it says what velocity I want. I'm going to type in 20. Look at all the other numbers in this list. When I press enter, we see that as I change my velocity to 20 meters per second, my CL dropped from point A to point 5. And this is something that can change. I can additionally change the air density. Again, the only recomputation is for the things that are interrelated. If they are not related, they won't be affected or recomputed. So for this condition now, I can go back by pressing enter. And if I want to save it, I can use the S command to save this into my cruise run case. But I'm going to execute a new run case, or this updated run case, with X. And now we see that when we have higher speed, our CL was reduced. So we have CL total of 0.5, but also we see that the elevator is less deflected. And our angle of attack is now at 2.4 instead of 5 degrees that we had set up manually in the run case before. We see that the efficiency hasn't changed much. And if we want to look at the CL distribution, we can look at the Trefftz plot by T command. And we can see the updated Trefftz plot. We see that the overall trend is the same. The only thing that is changing is basically the values that we looked at, the alpha that is changed, the elevator that is changed, CL that is changed, but because we're still at trim conditions, our moments are kept at 0. So this is one setup you can do. So this is just to automatically set up a trim flight condition or a turn flight condition using the C1, so level or banked horizontal flight constraint. We can additionally use C2 submenu to set a steady pitch rate looping flight constraint. So to do so, if we go back, we see that in the C2, now we have these properties, and what we could change are now these parameters. So let's go back and try to change these instead. So we're going back to the menu. We're going to exit the Trefftz plot by pressing enter, going back to the operation menu. This time we enter the C2, or steady pitch rate or looping flight constraint. And now we have this information. So what we can change here, we see the setup of the menu is a little bit different. So now we have the turn radius of 40 meters, the load factor of 1. So this turn radius is now already set up automatically. And we have a velocity of 20 and CL of 5.5. So let's say we want to change this now to velocity of 30 meters per second. And we see that the load factor is now automatically updated and the velocity is updated because now we're under new looping condition. And if I go back, so press enter to go back to operation menu and then press X to execute a new run file. We see that we have a little bit of change here. And we have a little bit of change in the alpha as well. And to look at the Trefftz menu, we can look at the Trefftz plot. So we can see in the Trefftz plot, we have again some updates, but they are minimal. But again, depending on what kind of flight conditions you want to simulate, either C1 or C2 submenus can be used to automatically recompute the interconnected parameters so that your simulation is set up properly. The next thing we're going to get to is the mode analysis or the dynamic stability analysis. We can get into the mode analysis by going into the operation menu or exiting the operation menu, going to the high-level AVL menu and typing mode. So if I go back to AVL, if I exit the Trefftz plot and then so we go to operation menu. If I press enter again, we go back to the AVL menu. And in the AVL, if you see from the very beginning menu, this mode is the Eigen mode analysis, which is what we can use for the Eigen mode analysis. So I'm going to type mode to enter the mode analysis. And we see that we have two run cases, so it is showing us the information for each of the run cases. And we are able to select all whenever they have this sign next to the run case, means they are selected. So this execution of the eigenmode calculation will be run for the ones that have this arrow next to them. Right now, all of them are selected. So if I press new eigenmode calculation, all modes will be calculated, or all run cases will be calculated. So to do that, I'm going to press N to compute the new eigenmodes. And we see that in the eigenmode analysis, we have various modes. So we have mode 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. We have 12 different modes. What each of these modes mean relates to which parameters are actually changing in those. So if you're discussing the stability analysis, looking at which parameters are changing in which mode can help you distinguish which mode relates to which properties, because these modes actually have individual names. So for example, you can have the phugoid mode, you can have the other modes that are related to the analysis of the dynamic stability for the aircraft. But in AVL, they are set up with numbers as mode 1 to 12. Technically, only 8 of these modes can be more relevant in general, but in reality, you do have the full 12 modes that you can analyze. So we see that there are some information for each cases. And we have two cases, run cases, and for each case we do have all the information for all the 12 modes for the aircraft. Now, how these information are related, if we go back to the slides, the way they are structured are the eigenmode analysis begins by considering that the unsteady flight variable ut consists of a steady baseline or the trim condition u0 or uo plus an unsteady perturbation which is changing with time. So the control variables d are also considered the same way. So you have your states and control inputs. U is some trim state value plus perturbation. Control input is some trim condition plus some perturbation. Now the perturbations are changing with u dot equals au plus bd. This is a simple state space model for any control theory. And each of these have 12 components. So the 12 components are set up with this order for your states. So these are the states related, the 12 important states for analysis of the aircraft, which are position, orientation, translational velocity, and angular velocity. Additionally, the control inputs, so the control vector components, which relate to the d parameter, are declared in the or related to how they are declared in your geometry file, because you can have as many or sometimes no control surfaces. And also they will be in the order that they are appeared. So if you first defined in your geometry file ailerons, they appear the first D or control input or D1. If you identified or defined the first control surface in your geometry to be rudder or elevator, they will be D1 in your control input. So they will appear based on how they appear in your geometry file if there are any control surfaces. So this is how these modes are related to one another. And the next important thing after the mode calculations is to actually look at them or examine them. So to examine them, we can use the X command here. So I'm going to type in X, press enter. And this will bring me this imaginary plane, which is basically having the sigma on the x-axis and omega on the y-axis. So this basically is the location of all the eigenvalues for all the run cases that I have for this system. Usually an imaginary number is equal to, we call them lambda here, or an eigenvalue is equal to sigma plus I omega. Sigma is a real part of that eigenvalue or imaginary number, and omega is the imaginary portion of that imaginary number. For stability, we need all the real values for all the imaginary numbers or eigenvalues to be negative or be on the left-hand side of this plane. We see that for this aircraft, we do have some points that are on the right-hand side. This means that these modes are not stable. So if you remember earlier, we were analyzing the static stability of the aircraft, and we found that this aircraft was not statically stable. Because it wasn't statically stable, it wouldn't for sure be dynamically stable, because that static stability is a precondition for dynamic stability. So we see that also when we get to analysis of dynamic stability, we see that we do have some unstable dynamic modes for this aircraft. Now, if we were to further examine these, we see that in the command window, it's saying that click on the root of an Eigen mode to be viewed. So we can click on any of these modes. So any of these dots that we see, you see that they are identified by color for which run case they are coming from. So we have run case 1 as red here and run case 2 as orange. And let's say I want to see one example that is a stable mode. So we have here a non-oscillatory mode because omega is almost 0 or 0, and it is on the negative side of the real portion, sigma. So because it has a negative real value for imaginary number or eigenvalue, this mode is stable. I'm going to click on this mode, and this will bring me to this window, which basically shows me some information. So this information that you're seeing here are related or replica of the information we saw on the AVL screen when we talked about the 12 different modes. So this tells me that this is a mode 2. Now what this mode is called and how it's related, you can basically find the naming conventions when you study further the dynamic stability of the aircraft and which parameters are involved in that stability mode. But we can also see them on the screen here, and this also tells me that this is from run case 1. Now when I enter this menu, in the main menu of the AVL, it is showing me some new commands I can use to interact with this menu. So I can turn left and right. So if I click this window, I can press left to turn it left. I can press R to turn it to the right. But something else that is interesting in this is that this is an animation window. So I can actually go back and forth in time using the smaller than or larger than buttons on the keyboard, which are used for the mode play you see here. So this is the useful information for the animation. So I'm going to use the smaller than. So we see that the aircraft is rolling outward and rolling back inward. And you see this scaling out to make sure that it is inside. So if we see that the scale is not properly set up, we can reset the scale to make sure that this is in the viewpoint that we can see. So I use the normal size, and I use 0 to go to time 0, and I use 1 to go to scale 100%. And this is basically to look at this mode. And let's see if we can look at another mode, so I'm going to press space to exit, and I'm going to examine another mode. So let's look at, usually you want to look at the modes that are on the left-hand side, so they should be more stable. So I'm going to look at this mode now. Or if we want to look at the further area here, what you can do is you can do a blowout. So if I press B, so I have to go back, I'm going to click here and then press exit to go back. I'm going to press B to do a blow up window. Okay, it looks like we exited to the main menu, so we're going to mode menu again. And then we already have the calculation, so if we press B, it says no blow up to show, so I'm going to go to examine, then go to blowout. So let's go to mode analysis again. We plot the routes. So we see the routes. And then we can do a blowout here, so mark off the corners. So I want to look at the ones that are closer to the origin, so I can see them better. Now I can see here what is happening. And now I can do examination. So I'm going to click on this mode now. And if I play the animation, you see that this is actually oscillating, but it is stable, so it's going back to where it's supposed to be. From the way it is behaving, we can tell that this is a Dutch roll because it reminds us of a skateboard or skaters on ice that used to behave like this or skate like this. That is where the Dutch roll name comes from. But this is actually something that you can observe and use your knowledge of the different modes for the airplane to be able to identify or map certain mode numbers that the AVL gives you, for example, this mode 4, and the naming conventions that you know for the different stability mode or modes, flight modes for your aircraft. So this should be everything that we needed to cover, and this should be putting all the information that we had learned together to come up with a design, the mass distribution, and how we can use them to analyze the stability of our aircraft, how it's performing, its behavior, what we need to do to change certain aspects to make our aircraft more efficient, increase, for example, its E or Oswald efficiency factor, make sure that it doesn't stall, make sure that it's statically stable, and check its dynamic stability for various modes. So that is all for the review of the AVL. We will have another tutorial to discuss how you can export the graphics from AVL and get vector graphics for any reporting or presentation that you may need from the AVL.